Alistair, Joe, Johnson. Strap yourselves in and feel the G's. This is our bioelectronics project. The design task for this project was to build a bioamplifier. Throughout this project we learnt that there is a right way, a wrong way, and then our way. The design specifications of this project were for the circuit to include one differential channel, an instrumentation amplifier, a second stage amplifier, and a driven right leg circuit, and also to have a total gain range from 1000 to 20,000 and an upper bandwidth of 45 Hz. We eventually decided to design the circuit to have the ability to perform as any of these to the right. Shown here is our final design schematic. First, looking at the voltage regulators. As the final prototype was powered with 9-volt batteries, voltage regulators were needed to regulate this supply down to 5 volts to avoid clipping on the 5-volt dual rail op-amps used. Immediately after initial signal input, the high-pass filter was implemented to remove DC shifting that may occur due to the use of batteries. The next section of the circuit considered is the instrumentation amplifier. Instrumentation amplifiers provide a high accuracy and stability, making the design suitable for biological measurements. Initially this was to be built by the team, but the idea was eventually replaced by using an off-the-shelf module, reducing the potential for errors in this section of the circuit. Driven right leg circuits provide relative grounding for the patient and restrict the amount of current able to flow through the electrodes into the patient's body. This was a necessary addition in order for the design to be safe to use as an ECG. This bandpass filter was designed to have a lower cut-off frequency of 1 Hz and an upper cut-off frequency of 100 Hz, as the biological signals to be measured by this design fall within this range. The amplifier acts as an isolation between the high-pass and low-pass filter, preventing any interference. As the instrumentation amplifier only provides a gain of 10, this part of the circuit provides an extra amplification of 100 times, making the amplification at this point in the circuit 1000. As previously mentioned, the design required this outline of variable amplification of 1000 to 20,000. So by using the potentiometer, we designed a variable amplifier that matched this requirement. In order to clearly observe an EEG, the output must sit between 0 to 5 volts. By using a DC level shifter, we're able to do so. Each individual section of the circuit was tested to ensure functionality and accordance with the design specifications. This is extremely important to ensure the design was fully functional before beginning any PCB design. Shown here is an image of the PCB in its final modified state that resulted from fixing issues that arose during the testing stages. The positive voltage regulator was not functional, and to solve this issue the design was powered off the board. The reference pin for the instrumentation amplifier was pulled to -3 volts rather than 0 volts, and to fix this issue wires were added to short the reference pin to ground. The wires were not on the board but were shorted together using wiring. The preamplifier was dysfunctional, and so due to time constraints, rather than addressing this issue on the PCB, it was built off-board. Overall, this project involved a steep learning curve. The time spent troubleshooting was extremely beneficial to understanding what design choices would be repeated and what choices would be changed. With little previous PCB design experience, producing the alpha prototype was a bit of a roller coaster.
This section shows our secondary stage of amplification, 100 times gain. Unfortunately U1B was entirely shot, so we ended up making it off the board. That's it right there. disconnects from the output from the differential amp bandpass filter, which is this one. It's got a gain of about 120, as well as clipping. Unfortunately, Johnson doesn't have any dual supply op-amps. Alright, stage 1, instrumentation amplifier. Have a 10 millivolt input and a 120 millivolt output, showing a gain of roughly 11, roughly what we want. Here's the PCB in action. Good times.